Okay, so on our foldable today, what we're going to work on is quantitative data for two variables. Okay, so go ahead and turn to the top of that. Let me get mine lined up. Okay, so first of all, let's just make sure we have some vocabulary. Remember that the explanatory variable is your predictor variable. Sometimes it's that word. We haven't really talked about that, so it's good to know that sometimes it's called that. Remember, that's your x-axis. Remember, explanatory has an x, so it's x-axis. And then you have your response variable. Spell that right. Which is your y-axis. Do not talk about them as independent and dependent like you would in a traditional math class. We have to use explanatory or response. And remember, quantitative data with two variables is when we had scatter plots. Okay, so there were some things we had to do with, excuse me, quantitative data. We had to, or with scatter plots, we had to be able to describe them. And remember, in describing them, there's some things you describe. You describe the direction, which is either positive or negative. And so it's where it's going. Is it going up or going down? You had to describe the form. And the forms we had were linear, curved, somewhat exotic, or no pattern. So an exotic would be like a sine curve, or maybe an or not exponential, but a cubic. Anything that has more than one turn would be something exotic. A curved is only going to have one turn. You have to talk about the strength. So it's strong, moderate, or weak. And in between, you would say moderately strong or moderately weak. So you'd have all those kind of in-between words too. And then you also have to describe any unusual features. And unusual features are if you see outliers, or maybe clusters or subgroups. Okay. And then we also had some other things. We also had some conditions we need to make sure we understand. So we had conditions for linear regression and correlation. So those go right here. Linear regression and correlation conditions. So the first one is that you have to make sure it's quantitative data, and most of it is, but you still have to say both sets of data are quantitative variables. You have to see if it's straight enough. And remember, to see if it's straight enough, you do the residual plot. And remember, residual plots are supposed to be random. So remember, residual plots should look random. If it's random, then that means it should be a pretty straight line. No really strong outliers. And then, does the plot thicken? And that is also a residual plot. Okay, so you can see all those things on the residual plot. And then there's a couple rules about correlation that we need to remember. I'm trying to squeeze them up right here. Correlation is -1 to 1. Remember, nothing past 1. Correlation has no units. It's only for linear. Your calculator will spit out R values for other things, but we have to remember we can only use it for linear. It's symmetric, So that means if I take my numbers and I switch them on the x and y axis, but I regraph them, the graph might have kind of a different slope, a steepness of slope, but it'll still have the same correlation. Okay? Not affected by changes of center. Or spread. Sensitive to outliers. That says outliers right there. And then remember, not causation. Remember, the only time you can have causation is if we do an experiment. Okay? All right, so there's the first half of everything we need to know about quantitative variables with two of them. Okay? Let's look at the bottom here. Let's keep going. Remember what a lurking variable is? A lurking variable is a hidden variable. That could be affecting the two variables. I think the most common example we talk about is that as kids get older in as kids go to a higher, get taller in elementary school, they become better readers. But the lurking variable is age, because usually as kids get older, they get taller. So it's not their height that causes the reading, it's their age that's causing the better reading. And so age is the lurking variable. Okay, remember we had to calculate things called the residual. And remember your residual is observed minus predicted. I would make sure that you write that down. If you're calculating a residual, don't say the residual is 5, do 20 minus 15 equals 5. Show that extra step. And then we had some equations which you actually have on the formula sheet. So y hat is equal to b sub 0 plus b sub 1x. B sub 1, which is your slope, was equal to r sy over sx. And then b sub 0 is y minus b sub 1x, mean, and that's your y-intercept. And remember, there was times that we had to manipulate things. So if they tell you what the slope is or they tell you what correlation is, we were able to do some manipulation to find other things. Remember, we did do something, if not straight enough, straighten it. Then you re-express. We did that a little bit. We didn't spend a lot of time on it because it's not supposed to be, or it hasn't been on the AP exam in years, and it's kind of a tricky process. But remember, we took like the square root of L1 and we saw if that made a difference for x, or we did the reciprocal, or sometimes we did the log, and we tried to make the line look straight. Okay, we still have a little bit more to cover here. So the next one is, what is r squared? So remember, r squared measures variance of one variable. That is predicted by the other. I had to write this small in a while. Okay, it's the percent of data that's closest to the least square lines. Percent of data that is closest to